Hello, and welcome to another one of Ethan's engineering videos. Today we're going to be working on Transport 1's Homework 4 Part 2, where we're going to be taking a rod and we're going to be setting temperatures across that rod, right? It's going to be at our room temperature. Then we're going to take that rod and we're going to put something really hot on both ends so that the temperature on those ends stays constant forever. And then we're going to simulate how this bar allows that heat, that difference in temperature, how the difference in temperature between the edges of the bar and the center at room temperature allows the heat energy to transfuse and diffuse throughout this rod, and we're going to simulate that over time using Python. So to get started, we're going to need to know what exactly, I don't want to pull up a text document, I want to pull up a code one, there we go. We need to know what exact equation we're actually using to simulate this. And I'm just going to write it out for you right here because we discussed it in class with Professor Coe. So I'll just write it right here. So the temperature at some position j at some time n+1, so this is 1 unit of time into the future, is going to be equal to the temperature at that same place, or not at the same place, at the place directly to its left at time n, plus the temperature at that place, that same place, place j at time n, and the temperature at the place directly to its right at time n. So as you can see right here, we're saying that the temperature at a certain place is equal to its old temperature plus the old temperature of its adjacent points, and how those two kind of push heat or pull heat from that central focus point that I'm calling the central focus point, which is at position j. However, those temperatures obviously don't add together because we'd be creating energy out of nothing in that case. So we have to weight each of these temperatures by a certain amount. So these edge two, the adjacency temperatures, are weighted by a factor R, which represents the thermal diffusivity divided by how precise our simulation is, which we'll get to in a second, and the current temperature of our central focus spot is going to be equal to 1 dot minus 2R. I don't know why I put the dot in there. I don't need to yet. So as you can see, this is our explicit differentiation. So I'm going to put explicit differentiation. And the reason this is explicit is because, because we're going to be strictly defining how accurate we want our simulation to be, and that differentiation directly affects how stable our simulation is. And we'll get to the stability and instability right at the end of the video. So stay tuned for that if you're interested. I've already imported what we're going to need for this. For this one specifically, we're only going to need numpy and plotly. This solve bandit is going to be used for later on in our video series for our homework for part 4. But again, if you're interested in that, you can stay tuned. So we're going to start by putting in the physical characteristics of this heat bar that we're looking at, this heat rod, that have been given to us by Professor Carlos. So I'm just going to quickly add those in. So the length of our bar, which I'm just going to use capital L, is 20 meters. So I go 20 dot, and then that's going to be notated in meters. We know that the thermal diffusivity, which I'm just going to call diff because I'm uncreative. The diffusivity of our bar is going to be 1 meter. Oh, I need to put, there we go, meters squared per second. So that's the units, it's meters squared per second. And then we have to specify how specific we want our simulation to be. So that comes in the form of this t, this j, and this n. Because what we're saying is that we're going to divide time and space up into tiny itty-bitty little increments. And we're going to move along our bar through time and through space along those increments. So depending on how precise those increments are, changes how precise our measurements and our simulation will be. But we've been given the increment for both of those, so we're going to put those in here as dx. So our spatial increment is going to be 1 meter. So we're only going to have 20 of them across our bar. And our time increment, our dt, is going to be equal to 0.5 seconds. So right there, I'll write that down. So you might be wondering, well, Ethan, you can use any of these numbers in the equation here. All you used was this r, because t represents the temperature at these different points j and n. So how exactly are we going to use that? And we're going to use that by defining r relative to these three numbers right here. So r is equal to the difference in time multiplied by the thermal diffusivity divided by our spatial area our spatial increment squared. Phew. Pardon me, I've got a bit of a sneezing fit because my room is actually around 40 degrees. You can see I'm wearing an actual coat right now, a full thick winter coat. But don't worry, that will not stop us from doing our transport homework. No siree. So we're going to keep at it anyway. So now that we have all the physical characteristics of our system set up, we have to actually start learning about our temperature. Because as you can see here, calculating each individual future temperature based off of three past temperatures from different places at different, the older time with weights is something that could be done iteratively, but would be very annoying and include a lot of for loops if we kind of did it the simpleton's way. So what we're going to use is np.arrays in order to make our lives a lot easier. So this is the part where we kind of set up our temperature rod, our heat rod, as a heat array, and then can kind of iterate across it. So we're going to make a new heat array called T. But what are we going to want to fill that with? Well, we're going to need the initial starting temperature, as I said before, the room temperature. So we're going to make that 25 25 Celsius degrees. So that's going to be the room temperature of our room. And so we're going to also need to specify how long our bar is so that we can make a bar out of that. So we're going to have n represent the number of increments in our array. And so we're going to make that an integer value, and that's going to be equal to the length of our bar divided by our spatial increments. Now, obviously, 20 is divisible by 1, since those are our two numbers here that we're dividing. I'm going to put the integer there just to be safe, to make sure everything's working correctly. Theoretically, we could use other numbers and it would mess that up, but again, we're only going to do stuff that's divisible. If we really want to change it and make the increments larger, we can, but I don't really think that's a good idea. So we're just going to do that and put the integer barrier there to make sure everything's staying safe and we're not accidentally getting any weird decimal stuff. So we're also going to need to specify our temperatures on the left and the right. As I said before, we're starting with a bar that is completely homogeneous temperature-wise at our room temperature, and then we're artificially setting the two ends at higher temperatures so we can watch heat diffuse through them. So we're going to make two new variables called T-left and T-right, and those are going to be equal to the two temperatures I picked. So we're going to do 80 degrees Celsius for the left, and we're going to do 65 degrees Celsius for the right. And now what we're going to do is we're going to make an actual array of temperatures. So the easiest way to do that is to just make T np.full, which creates an array full of a single value. So our single value is going to be our room temperature. And the first thing needs to be the length, the shape of our array, which in our case, if we feed in a single integer n, that'll just say it's going to be n spaces long. And the integer we're going to want to fill across that array is going to be t0. So if I open our variable array, we'll see we have t here, which is an array full of 25s, and there's exactly 20 of them, which is what we'd expect. But now we want to set those two n temperatures to be those artificially hot temperatures we created before. So we're going to say T, our temperature at index 0, and our temperature at index -1, which represents equally 0 is the first index in our array, and -1 is the last index in our array, no matter what. We're going to set those to be T left and T right. And as you can see here, I'm using unpack notation, and if I run this, it updates our T array, and you can see that 80 and 65 are now firmly planted on the ends of our array. So now our temperatures are all set up. We can actually plot this really quickly. So I'm going to do fig1, just to show you what our temperature bar looks like graphically. It's going to be equal to make, not nmake, just make underscore subplots. And then we're going to run fig1 dot, oh, a new line, please. Fig1 dot, come on, dot add underscore scatter. There we go. And we're going to want x to be equal to, well, we just want a range, so np a range from n, so there we go. Sorry, I had a little dust on my keyboard. And we want our y to be equal to our temperature, not t0, but our whole temperature array. And we're going to want our mode to be equal to lines. And then finally, if we can we set a template here? No, that's fine. Okay. So then all we're going to do is we're going to fig1 dot update layout to be template equal to plotly underscore dark, so that it doesn't burn my eyes in my dark bedroom. So we run this, and there you go. You can see our bar. So the left has a temperature of 80, The right has a temperature of 65, notated by 0 and 19, which would be their indices in the array respectively, and then all the center is 25. So that's good. It's exactly what we'd expect. We're also going to name this one. We're going to set name equal to 0. So now, when we run this, our graph will be named. Obviously, it's not going to show up now when we only have one, but when we have multiple, because we're going to be graphing this as we do our simulation, it will be able to be identifiable, and we're going to be able to see our time difference. So now, we're just going to, I'm going to do something really quick for housekeeping, and I'm just going to make something called t_reset. T_reset is going to be equal to t right now. So that way we're going to have just our t variable saved. So I'm just going to set this and t is equal to t_reset. So that way when we rerun this, we don't have to run this code all over again. We only have to reset our plot. And then we can run our for loop right here, because that's what we're going to do next. We're going to get onto the actual simulation. So what we want to do, obviously, is simulate a certain number of simulation sessions. So we're going to do for I in range. And the range we're going to look at is going to be from 1 to some really big number. So say like 5,000. That's a pretty big number. That looks like 50,000. I only want 5,000. 5,000 is plenty. So we're going to, for this range, oh, I have a couple extra lines already. So tab. We're going to want to iterate our temperature array based off of this right here. So how exactly do we do that? Well, the first thing we have to look at is how we can slice arrays, because instead of, again, for looping through every single one of these and then adding up the 2 on either side of it based off its index and then yada, 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 that would kind of suck and be horrible. And that's why we use arrays, is so we don't have to do that. So we're going to have to use slicing, so we're going to take a quick look at that. So again, our t dot size, if you remember, it's 20, right? It's 20 indices long. So if I were to tell it to slice it across the whole thing, obviously I'd get all of our arrays. If I were to say from 0 to -1, since again, 0 is our first indice and -1 is our last indice, you'd think that it would match t as it is written before. But that's not true, and that's because slicing is non-right side inclusive. So even though theoretically the start point is 0, and if you get rid of a point specificity, it goes to the start point, and the end point is 0, and if you get rid of that, it ends at the end. Adding this -1 here changes where it stops. However, if I were to add a 0 here, that would not change where it stops. So we just have to keep in mind that the right side index tells us the first entry which is not included. So we just have to keep that in mind. So what we want to say is we want to change only the temperatures that are going to change, which are all of our temperatures except for the N2, because again, we're holding them artificially at their own temperature. So temperature, using what we just learned, we want to slice it to say 1, because that would be the second array, indice in the array, to -1. Now, -1 is the final temperature, which is also constant. However, we remember that slicing is non-right side inclusive. So we have to remember that we're not going to keep that. So now I'm just going to copy this down here, but I'm going to get rid of all these parentheses, obviously, because we don't need them right now, but they will become important later. So I'm going to add the dot, and I'm going to add the dot times, so that way that's algebraically correct. So now this is where we have to slice these to make sure we fit our jn minus 1, our jn plus 1. This should be a plus 1 right there. I realized I didn't catch that. And our original temperatures. So obviously, since this is the temperature range we're looking at, these are the temperatures that are actually going to change. These are the outcome of our focus point, our central points after one time iteration, so we're going to need to have their old temperatures there as well. So that's going to be our middle point, is going to be the exact same index as what we're outputting each time we iterate. And then I'll just paste it here and here for both of these. So now we're going to move left and right, correct? So if we're starting at indice 1, which is included, we want to go to the left one, so prior, so we're going to want to go to 0. And since -1 doesn't include the last indice, we're going to move 1 over to the left as well to get us to -2. So that means that we're including the first array, but we're skipping the final 2 arrays in our temperature set. And we're going to do the same thing over here, but for the opposite. Instead of going to the left one, we're going to go to the right, so towards our 65 value instead of our 80. And so instead of excluding just the last value, we're going to want to exclude the first 2 values, 0 and 1, because 2 is included. And we're going to want to include all of our final values. Since -1 tells us we're actually excluding the last value, if we just get rid of it, like I showed you before, that will include our final value. So now every time we go through this for loop, we're going to iteratively update our temperature one further dt, which is what this n is. N represents the integer number of dt's we've traveled into the future, one of those iterations away. So this will iterate through. But obviously we don't just want to get what the final temperature array looks like. We want to have a kind of a signal of how far we've gone. So we're going to do a little plotting, a little bit of plotting, a little bit of mischievous plotting, you might say, as we go through time. So what we're going to do is we're going to add an if check right here. So if I, which represents the integer number we've gone, has a modulus, which modulus represents the divisor after division. So 6 divided by 4 is 1.5, obviously. But because we're dividing by 4, that remainder is 2 out of 4, right? That's where we get the 0.5 from. So the remainder of 6 modulo 4 would give us 2 as an answer. So it tells us the remainder of division. So if I divided by 25 does not have a remainder of 0, so if it's not an even value of 25, we don't really care. But if it is an even value of 25, which is why that's the reason why we're starting our range at 1 and not 0, because 0 divided by 25 is obviously 0, and there's no remainder, so that would plot the second one again, which would just be not super helpful. So that's why we're doing it outside, and we want to plot number 5000 anyway. So I digress. We're going to want to plot this. So I'm just going to copy my add scatter right here. So fig1.addScatter, np range is the same. Our y is going to be our t again, our lines, but our name is going to be an f string this time, so that way we can put in our value, and our value is just going to be I. Oh, I want that to be inside. So we're going to name our plot, our specific line on our plot at least, whatever integer number of iterations this is. So we're going to run this, and it's done. It ran really quickly, and that's the bonus part of using arrays. So now we're going to pull up fig1, and hopefully it should look very beautiful. And there we go. So as you can see here, we're starting with our same starting point there from 80 and 65 with 25 all in the middle. And as you can see, over time, slowly we get the distribution of heat across both of these points. And it very clearly approaches a straight line, which is actually sort of what we'd expect. So I think if I scroll down and control click, oh, there we go. You can see right here, we have, did I zoom in somewhere on accident? I think I zoomed in. Auto scale. Zoom out. What did I do wrong? Oh, it's because I keep 0 in as well. Oh, son of a gun. There we go, auto scale. Okay. I'll run this again. 0. Click not 45. After 400, it does seem to mellow out. So honestly, we could knock a clean 0 off of this. So this resets t included. Run this again. T reset did keep its value, correct? Oh, did I never run this? Because the whole point of running this was that I wouldn't have to. Son of a gun. Why is my variable inspector not working? Come on, there we go. Okay. Anyway, so we knocked it down a little bit. We don't actually need 5,000 iterations. Come on, I'll click you. I want 425. There we go. Okay. So now you can see here the evolution from 80 to all 25s up to 65 to a nice even straight line, which shows an even temperature distribution. The heat no longer really has anywhere else to flow. It's just kind of radiating to the environment according to our simulation, which does make sense. The differential between the 80 and the 65 is a gradual slope, no longer these sharp turns, and we've achieved our goal. So this was hopefully a bit of a shorter video. It only looks like it's around 20 minutes with a bit of my synchronization clips that I'm going to cut out at the end. But despite that, I appreciate your attention. I appreciate your focus. I hope to see you in the next video. But until then, thank you, and have a good evening.